get this started. So thank you, David, for the introduction. Today I want to tell you a bit more than I did earlier today about the center and some of the research that we're doing here at the center. And let me just start by showing this figure, which pretty much shows the Dutch physics complex. This figure was actually taken by a drone right after Ringhole was finished. That's why there's no grass and there's still some construction left here. But the main thing here is to emphasize that this, the Dutch complex is actually composed of Nielsen Hall. This is where we're standing right now. We're actually somewhere back here. And this used to be the building where all of physics and astronomy was housed before we had Link Hall, which is this building where we had the dedication area today and the lab tours. And this building is where now the Center for Quantum Research and Technology is housed. So the mission of the center, there's three main pillars of the mission of the center. As we heard this earlier today, one of the goals is to become a world-class research center. So it's one of the pillars that we have. But in order to accomplish this, we need to do more. We need, students are an integral part of this mission. They help and do a lot of the research that we do in our groups. By having this center, we're able to offer them a broader educational perspectives. We're able to make them leaders and hopefully train the next generation of workforce that we need for this field, as well as prepare them for future careers. The other aspect of the mission is that we want to establish partnerships with industry. And the reason to do this is that we can perform the fundamental research that is needed for these area of quantum technologies, and through partnerships with industry and national laboratories, we can then transfer this technology out of the lab and into actual devices that have commercial applications. By partnering with industry, we also have a route for students to participate in industry. Through the center, as I mentioned, we will aim to train the workforce then that can work with industry. So there's going to be a synergy between these three main pillars that we hope will make the center a success. So let me back down a bit and talk about the research that we're trying to do. So as you know from the name of the center, there's this word quantum technology, which we've heard many times today. So the main goal of the research that we do is to use quantum properties to enhance devices and develop new technology. So some of these properties, as we heard this again earlier today, are superposition and entanglement, and I will now try to give an explanation for these two things. Hopefully I can do a good job. So explaining these two things is actually complicated without really diving into quantum mechanics, but there's one particular, let's say, classical picture that helps us to get some intuition that I like quite a lot, which is in this book. Recommend you to read it if you want to learn a bit more. But let's think about having a cube. So if we take this cube and look at it, what do you tend to see? What you tend to see is to have either one surface or the other surface of the cube be in the front. So you can think of this as the cube being in a sense in a superposition of these two states, having one surface or the other surface in the front of the cube. And then once your eye focuses on one of those, that makes it the choice that you see. What about now taking this and extending it to two cubes? So what do people see? So typically, unless you work really hard, what you tend to see is that both cubes have the same surface pointing forward, either this state or that state. So once your eye focuses on one of the cubes and you kind of see one state, then the other cube kind of automatically comes to be in the same state. And this is still kind of in a superposition such that you don't know which one you're going to see. If you look at the cube multiple times, you can see one or the other. But once you know the state of one of the system, that is, once your eyes focus on one of these surfaces, the other one seems to follow and give you correlation. So this kind of, in a nutshell, the ideas of quantum entanglement and superposition, in which we have correlations that if we measure something about one system, we can say something about the other system. So with these ideas in mind, people have been trying, us among many others, to use some of these properties to enhance devices. And again, this brings down to this idea of quantum technologies. And of course, this is nothing new. People, and many of us here, have been trying to do this for a long time. But this now is becoming, let's say, more trendy due to the fact that of the applications that can come out of this and the promise that comes out of quantum technologies. So I would say there's already some things that have come out of this search for developing devices. One of them is the atomic clock, which is one of the most precise devices that humankind has ever made. They're able to keep time with an incredible precision. And moving forward with the technology part, people have been able to take this complicated apparatus that takes a whole table and a lot of lasers into something that is compact and available commercially. So now you can actually go out there and buy an atomic clock, of course not with the precision we have in the lab, but nevertheless you can buy an atomic clock and use it for applications. Another example of what has come out of this technology is in terms of what quantum information, or the idea that you can transmit information between remote sites in a completely secure way. So this has applications in security. Banks, for example, want to use this. And it turns out that quantum technology, one of the things that is promised from quantum technology is this idea of quantum computers that can do factorization really fast. And most of the encryption today is based on factoring numbers. So if anyone was able to build a quantum computer, they would be able to break the encryption codes. However, using quantum mechanics, we can get around that problem, and companies have actually started to develop these systems and offer them commercially. I would say one of the areas that is coming, but is not as developed, is the one of using quantum resources for making more sensitive measurements. And probably all of you have seen or heard about LIGO, where they're detecting gravitational waves. And they're now actually using quantum states of light to make these devices even more sensitive, so they can make or see more events when they perform measurements. This extends to other things like measuring electric fields and with plasmonic sensors to measure chemicals and other type of materials that you might have. And if anyone has been watching the news this week, probably you have seen that Google announced that they are able to do this notion of what is called quantum supremacy, where they can use a quantum processor to do processing a lot faster than you can do with a classical processor. So all these ideas are coming, and there's a lot of work that is being done in this area. So one of the areas which the center is focusing on, and also one of the areas that I think will have an impact in the shorter term, is this one of quantum enhanced sensing. And this is also kind of simple to understand how it is that we can actually get an enhancement when we use quantum resources. So one of the things that we get from these quantum correlations between the systems is that the noise properties can actually be lower than what you get with a classical system. Let's say a laser beam or something along those lines. So in that case, what happens is that you're going to be limited by this classical noise. So typically when we perform a measurement, what we have is a signal, which is shown here by this peak, and then we have noise, and that noise limits the smallest signal that we're able to detect. So what happens is that this noise is actually a fundamental limit with classical light. We cannot go below that with a classical system, but through the use of quantum resources, we can actually get less noise and then just resolve the signal better. But when this really becomes important, when we have really, really small signals that we're not able to detect with a classical state. So in this case, we have small enough signals that we're not able to see. Once we use the quantum resources, the signal appears again and we're able to detect it. So this leads to this idea of being able to detect signals that are not possible with classical devices. And again, this will have applications in many fields, and it's expected that quantum technologies will have an impact in almost every aspect of society. For example, quantum enhanced sensing, think about what you can do with this. You can actually detect maybe a disease earlier, or you can detect a threat or something like that. So there will be, of course, application in the health sector. In terms of quantum computing, what I mentioned, cryptography, being able to transmit information security, there's of course a lot of applications in national security, and the list goes on and on. It's a really, really long list. As a result of this, it's expected that this field will have a really significant impact in our economy. As David mentioned in today's, before the event, by some, sorry, this pointer just keeps going in and out. So by some estimates, This is expected to be a multi-billion-dollar industry in the next 5 years or so, and expected to grow to over $1 trillion industry by 2040. As a result of this, there's significant investment by many companies and also governments, not just in the United States. Here in the United States, the federal government has launched the Quantum National Initiative to support many of these efforts, but this is something that pretty much all the big players, a lot of governments and a lot of countries are pushing forward. And one of the things that makes this area quite unique, I think, is the investment really early on that extends outside basic science. The fact that industries are jumping in at this stage of the game is pretty impressive because we're still at a stage that we're trying to understand all the basics and the foundation of things and how to combine everything to really take advantage of the resources. So as I mentioned, Google's one of the companies that is doing this, but it's not the only one. IBM, Microsoft, all the major companies are diving into this idea of getting a quantum computer. And there's also a lot of startup companies that are trying to look and explore some of the most applied aspects of quantum technologies. So just to dive in a bit more on what the research entails, in order to get this a bit farther and really take advantage of the technology, we need to use different types of systems. And we won't go into any details on this graph, it's a bit complicated, but the main point to emphasize here is that we will need to have a collection of many systems working together to really take advantage of the technology, and we need to make them work together in such a way that we take advantage of the unique properties that each system has. For example, we need to use light, atoms, mechanical systems, solid-state systems, superconductors, spins in a solid, and again, it's a long, long list. Each of these systems has their own unique properties. So the work that we're doing here at the center, part of it is to develop the fundamental understanding that we need to control and use these systems. And the other one is to build interconnections between the different systems such that we can actually, again, take advantage of the properties of different systems and make them work in a way that we can take advantage of them for applications. So coming back to the center itself, the focus is going to be on fundamental aspects of quantum technology with the idea of getting applications in the longer term in terms of sensing and quantum materials. This will give us the opportunity to interface with companies. As I mentioned before, the idea is to develop the fundamental understanding of systems here, and through the interaction and collaboration with national labs and companies, we expect to be able to